Today we're going to continue our discussion of analysis of variance, and we're going to talk about repeated measures. And the repeated measures for this week are going to be calculated from using the general linear model. This is a least squares model. In the next video we will talk about repeated measures using a maximum likelihood method. And that would be SPSS's mixed model. I'm going to go through this fairly quickly because, as it turns out, there is a very good book, Performing Data Analysis Using SPSS. That's an e-book, and you will want to refer to chapters 51 and 53 for further discussion of this topic. All right, so our data set that we're going to use is our Ortho-K data set, and just to recall, there's a subject, we have some basic information, but basically it's about lens types. Lens types were either spheric or aspheric. Later we talk about lens type 2, which is aspheric, and then spheric that was a good lens controlling growth, and another lens type that was not so good at that. And in this data set, this is a matched data set using propensity analysis. We're going to talk about propensity analysis and create this data set in a few weeks. There were two eyes. Both eyes were used, and there's a separate line for each eye. So we have, well, it doesn't really show it very well here, but left and right eyes. Then a number of baseline eye characteristics. And then note the horizontal layout of axial length. It's axial length at baseline, 0, after the first year, second year, third year, fourth year, fifth year. This is what we mean by the concept of repeated measures. Now, so we're measuring the same subject ID 6 times. Now, one thing, this layout, so what we have to take into consideration here is these are not all independent measurements. They're correlated with each other because they're the same individual. The data comes from the same individual over repeated times. This violates our basic analysis of variance assumption, and we'll have to take into that account. Now, using the GLM procedure, we do, in fact, have to have the data laid out in this horizontal fashion. But you'll notice that we also have repeated measures, or blocks, it's sometimes referred to, in terms of the eye. So there are some people with left and, or not everybody matched. After we've matched the data set, we don't have all left and right eyes. But that's another thing to consider, and because we want to, it's actually less important in this particular case the way we did it to worry about this. But if we were just collecting data and we had left and right eyes from people, these eye is not independent, and we have to take into consideration the correlation between those two. But because it's laid out this way, vertically, we can't use the GLM to do that. If we were going to use GLM in this case, then what we would do is we would have all the left eyes, AL1 to AL5, 0 to 5, and then we would have all the right eyes, AL0 to AL5. So we'd have 12 columns. We don't have that in this case, and in order to get rid of this lack of independence by eye, we're going to split the file and do it twice by eye. Again, this data set's a little different in that the way it's laid out, we could actually ignore this, but we're not going to. Alright, so now you see that our eyes are all split. There's all the left eyes and all the right eyes. Alright, so let's do this. Now we go to Analyze, General Linear Models. Now, we in the past have used univariate to do analysis of covariance and between subjects analysis. But now we're going to go down to repeated measures. So we're going to have year. We're going to create this variable called year. And it has 6 levels. Baseline plus year 1 through 5. And we add that into there. We're going to define it. Now, we now are within subject's variable has these 6 variables down here. And so we're going to go from AL0 to AL5 and just set those in there. Now, if we had the left and right eye also laid out horizontally, we'd have all left eyes, AL0, columns for that, and then all right eyes, 6 more columns for that. And then the model takes, so order is important. If we did right AL0, left AL0, right AL1, it would be different, wouldn't work as well. This, I'm pretty sure that the slow-moving variable is the bigger one. Slow-moving meaning that there's 6 levels of left eye and 6 levels of right eye. But we're just going to do that for now. And in chapter 51, it talks about a one-way repeated measure analysis of variance. In 53, it talks about a two-way, and we're going to do that. So we're going to add in, now we could put in lens type, which just has 2 levels, or we could put in lens type 2, which is 3. Actually, let's go ahead and do that. So here we go. And we don't have any covariance. Our model is automatically set up for full factorial, so there's nothing else we have to do with that. We can go to options, and we can do homogeneity tests, we can do descriptive statistics. There's a number of other things that we could do. And we want to display the means for, I'm not sure exactly what I just did, but could display means for these. And notice it says compare main effects. Unfortunately, we still don't get that interaction. And the authors of the text recommend using Bonferroni. I'm still a least significant difference kind of guy. And let's hit continue. Okay. Then we get this output. It tells us our dependent variables are the axial length from 0 to 5. We get a separate analysis for the left and right eye. There were more left eyes in the sample than right eyes. That's from our matching process. When we matched in this set, we matched separately for eyes. In the descriptive statistics, we get the raw means for everybody, and standard deviations, and the sample size for both the left and right eyes. And then here we have Box's test of equality of covariance matrices. We actually want that to not be significant, and we see that it is, which says that our assumption of equal covariance matrices, the items in it, is violated. This is a multivariate test. This uses, instead of like year being a fixed independent variable, it puts all 5 years, 6 years together and creates a test just using all these going across. It just does it a little differently. We don't normally use this. Matrices test of sphericity. So the assumption is, if we were to, the assumption is when we do this test that all the items are correlated equally with each other. So year 0 is the same as 1, 1 is the same as 2, 0 is the same as 2, 0 is the same as 3 and 4, and so forth. Also the variances are equal across all the years. And this tests for that equality, and we can see that it has been violated because we've rejected the null hypothesis of equality. And so we can now look at something that's called the epsilon. Now what epsilon says, if you refer to your little brief, it gives you a hint here that the Hunt-Felt is the least conservative and used when epsilon is less than 0.75. And so we can see that epsilon is less than 0.75, so we're going to use the Hunt-Felt correction. Because when we come down here, remember in the t-test we had when variances were equal, use the top line. When they're not equal, use the bottom line. Well, here there's 4 lines. And when we violate that assumption, we want to use one of these 3 corrections, the Greenhouse-Geyser, Hunt-Felt, or lower bound. If it wasn't rejected, we could assume that sphericity was true, and we could use that top one. Now, the thing to notice is that the sphericity assumed, the mean square error is the smallest, and it gets bigger as you go down. In this case, we want to use Hunt-Felt, so the mean square error term is going to be 41.134. But as it turns out, the degrees of freedom are adjusted, and the F statistic is the same. So, but the significance is based on the degrees of freedom. So the F values, the P values could be different, but the F statistic is the same. All right, so we look here, and it says that year is significant in both the left and right eyes. So then, because the year has an order to it, if we had done eyes, well, there's only 2 eyes anyway, but eyes have an order to them, so 0, 1, 2, 3, 4, 5 makes some sense. So we look for a linear trend, a quadratic trend, cubic, and then the 4th and 5th. We have 6 variables, so we're going to get 6 tests. And we see that for the left eye, the linear trend was significant, meaning that axial length tended to go up. Quadratic was also significant, and that means that there was a bend in that data. So it might have had an arc to it that kind of went like that. The same way with the right eye. And year by lens type was also significant and had these trends as well. In other words, they in the interaction effect, they diverged in a linear and quadratic way. they diverged a lot at the beginning, and then there was a bend, so their divergence was reduced. So if we're looking at, let's see if we can draw something. So we have, say, the spherical lens. The divergence is going like that, and for the spherical lens, oh, well, no, this is the interaction, so it's both of them. So the divergence is actually, let's say it goes like that. Actually, that's kind of what the actually, it doesn't look like that, but that's the idea. That the interaction means that these guys are diverging more as time goes on. It's linear because it's going up, but it separates faster. There's this bend in it, and it either separates faster or it slows down. It does one of those. You have to actually plot the data to see how that works out. Okay, then we have our familiar Levine's test, which we remember from the t-test. And this checks, and it says variances, at least in the left eye, are different for almost every year, whereas they're not so different for the right eye. The between subjects is lens type 2, and that's significantly different in both cases. When we look at this, we get the estimates for the left eye, the aspheric, spheric, and spheric, and the right eye. And when we do pairwise comparisons, for the left eye we have aspheric versus spheric, aspheric versus spheric that grew, no growth versus growth. And we can see that there's a big difference between aspheric and spheric. Actually, we could say there's a significant difference. We don't know if it's big or not until we calculate effect size. But there's no difference between aspheric and spheric growth. Same sort of thing down here with the right eye. Years, here we could plot the years. We could bring that into Excel and plot these by year. That would be a good thing. And we can see that actually the years for the left eye are different all the way down the board. So axial length, the overall collapsed across lens type, axial length grows each year. All right. So here we see the, you can see this is starting out at 24.5 and it goes up to 24.9, 24.9 up to 25.405. So there's growth in both of these. That's about it for repeated measures.